Thank you for the kind introduction, Kun. Also, I would like to thank HiPEAC for inviting me as a keynote speaker. This is the outline of my talk. So I'll start the talk by just introducing Pragmatic and our unique technology, FlexIC technology. And next, I will define what bendable computing is in the context of emerging applications, what we call extreme edge. And then I will shift my focus to bendable processors. So we build, which is the core element of the bendable computing. So I will present some of the prototypes we build in the domain-specific and general-purpose processor domains using FlexIC technology. So after that, I will deep dive into our latest work, which is the first bendable RISC-V processor. And I will end my keynote by just talking about some of the stuff we are doing at the moment, and also I will be reflecting on the challenges and lessons learned during our journey, especially when facing a new technology like flexible electronics. So just a quick introduction to Pragmatic. So we are located in the UK. It's a UK company. We fabricate flexible integrated circuits. So in short, I use the term FlexICs. So the word flexible here should be taken literally. So what I'm saying is not programmable, but it's physically flexible or bendable. So the unique property is that it's ultra low cost because of the low cost manufacturing process we have. And as I said before, we are in the UK, so we have two sites, headquarters in Cambridge, which is where I am, and the design happens there as well. And our fab is in Durham, which is a city in North England, and this is where the manufacturing takes place. So we are about 350 people. You can see some of the investor information there. Again, very quick introduction to the technology. I brought some sample here as well, so just to show how they look like. So our FlexIC, we manufacture the ICs on flexible wafers like this. So this is a standard 200 millimeter wafer. And there's lots of chips. The chips are diced. When they are diced, they look like this. Let me get the laser pointer here. Yeah, they look like this. So the specific of this technology is that it's not silicon. So we use it's an inorganic material, metal oxide called IGZO. In short, we call it IGZO. So it stands for indium gallium zinc oxide. And so we have the devices like N-type transistor, so which is based on thin film transistor technology, so it's slightly different than the conventional MOSFET. You can do the transistors, resistors, capacitors, so you can actually build a logic and any type of digital analog mixed signal circuits you can design with this process. So we have industry standard 200 and 300 millimeter fabrication. And the substrate is called polyamide, so that's extremely thin, less than 30 microns. So that makes it so flexible and bendable. And in 2024, so we opened our first 300 millimeter fab, which is located here. Actually, it's a huge warehouse. One of the fabs are here in red, but that we will populate the entire warehouse with different fabs over the years. And this is also the first 300 millimeter fab, semiconductor fab in the UK. So let's look at the design fabrication. I get these questions a lot, so do I need to do anything special to use your technology? No. So we provide PDK. We have standard cell library, and they are enough to enable to be integrated into commercial EDA tools, so you can design your chips as if you are designing for other foundries. So from that perspective, it's no different. If you're designing silicon chip, you can also design a flexible chip in the same way. On the fabrication side here, we are different. So most of you know, if you tape out today in silicon world, tape out and you get your chips, it will take months, maybe 6 to 9 months, depending on how the priority customer you are to the foundry. But in our technology, it takes less than 4 weeks. And we have also plans to reduce to 2 days. So this is a game changer. So you tape out something, and 2 days later, I'm giving an example, so I picked the 2 days here. You get your chips back. So this is not possible in today's technology. And also in terms of sustainability, so our fabs use much less water, use less energy, and the carbon footprint is a lot smaller than conventional fabs. Very quickly, I get this question as well, the pragmatic business model. So we are exploring different business model. The one on the left is what we call integrated device manufacturer. That means we are designing and fabricating and selling our NFC near-field communication chips for inlays. But the middle one is where we like to be in the future as a foundry. So, which means that, we work with the fabless partners, they bring their design, we fabricate and sell just wafers. The last one is also interesting. We haven't actually explored this, but what we call it as a fab as a service. This means that we can actually replicate our fab and move it in and paste it, like a copy-paste, paste it somewhere else on a partner site, and then that fab just churns out chips for that partner, for that specific part. So that allows the partner to have the sovereign capability in terms of fabricating FlexICs. So let me talk about what bendable computing is and what's the motivation for that. So before I define what bendable computing is, so I would like to introduce the concept of extreme edge. So this is a term we coined. So it's a domain where a computing system deployed in there cannot be based on conventional electronics for several reasons. So some of them are like quantitative factors like power and cost, but some, and these are more important, because of the qualitative constraints like form factor, conformability. So what I mean by conformability is the electronics is taking the shape and the contour of the surface. For example, if it's a body, it has to conform the surface of the skin, and comfort. So these are important constraints. So I'll give some examples about the applications at the extreme edge. So the first one is FMCG. So that is fast-moving consumer goods. So these are the daily things we consume, like drinks and foods and etc. So smart labels and smart packaging there is a good example where the FlexICs can be integrated. Smart swatches, this is more in the personal care, so I have more details on that. On the healthcare, I think this is a very interesting area, but these are more like a fast consume healthcare goods, like smart patches for ECG or EMG or EEG monitoring. smart dressings like the wound monitoring. Today, if you notice, there is no electronics in the Band-Aids we buy, so there is a reason for that. Then most recently, this is a bit niche, but smart ingestibles. So you take a capsule or something you ingest, and then it monitors the activities in the stomach or the intestines. And on the far edge, so the e-textile, smart textile is another area that is very interesting to integrate electronics into garments and carpets. The last one is agriculture and environmental monitoring. For example, here is that there's a picture of a plant, and I don't know if it's visible clearly, but here there is a flexible chip, wrapping around the plant to monitor the growth of the plant. Now let's look at what type of computing devices needed for extreme edge. So there are some capabilities and properties needed. So we call them bendable computing systems. So they are it looks like a regular IoT device, but the difference is that all the components are shown in that diagram are based on printed or flexible electronic components. For example, the sensors are printed sensors. These are super low-cost sensors. Typically, they are manufactured using screen or inkjet printers. There is printed batteries, energy harvesters. There are companies who are commercializing these bendable. Some of them are paper-based printed batteries. Electronic displays, I think these are most of you know about that, so e-paper displays are already in the market. And finally, FlexIC doing all sorts of things for the interfacing the sensors with an analog front end, memory, processor, communication, possibly wireless communication like NFC or UHF. So this is where Pragmatic plays. So these are the things like, sensing, memorizing, processing is one thing. The other one are the more of the other qualitative properties, like it has to be super ultra low cost, because a lot of the applications at the extreme edge is cost sensitive. And energy neutrality if you have it, is great. That means that you don't need a battery, but you have energy harvester, and you're harvesting energy from the environment. Conformable, I described that before. It has to take the shape of the surface. Possibly stretchable. Some of the things require stretching, maybe like if it's a wound monitoring dressing, so that it can be stretched, and the electronics should sustain the stretchability there. And one of the most important ones, the thin form factor that's required for comfort. So you don't want to have a patch here with a bulky electronics, bulging out. And the other thing is that these are very sensor-driven applications, and sensors don't run very fast. They run at the hertz or kilohertz level. So so actually you don't need the processing at a very high speed, like megahertz level. So you may disagree with me, but I will show some examples for that. Just quickly here, this is the taxonomy diagram, and the blue ones, so it shows the general purpose as well as domain-specific processing. So we explore, the ones we explore at Pragmatic and along with our partners are shown in blue. So on the general purpose front, we build legacy ISA like 6502. I will present that. We build ARM processor. We build RISC-V processor, which I will talk a lot today. On the domain-specific one, so we explore the additive one. So what I mean by additive is that you are designing ground up instead of taking an existing design and subtracting things. So I will talk more on the ASIC and hardwired. So what I mean by hardwired is that it's not programmable. Is there anything I need to, yeah, okay, move on. So let's start with domain specific. So this is a project, it's an example of domain specific processing element. We built a hardware ML. So the project name was plastic armpit. There's a reason for that. This was a collaborative project between ARM, Pragmatic, University of Manchester, and Unilever. And it's, the application is related to personal care. So it's more on the deodorant. Coming from the deodorant use case. So for Unilever, it's very important to understand the consumer perception, the correlation between the consumer perception and the human armpit malodor, so that they can improve, they can measure this correlation and improve their new deodorant products. So what they do is they organize these armpit sniffer panels. So what they do is they on their payroll they have human beings called super sniffers. So all they do is go and smell the test subject's armpits and score how bad they smell. So and they are chosen to be very they have a very ultra sensitive nose, and this is what they are paid for. And it's very important to improve their deodorant or perspirant the products. So they organize these panels across different geographies in the world, so it costs money. So the idea was, can we actually build a smart swatch consisting of some flexible electronic bits, the conformability and the extreme thin. It goes to the under armpit of the test subject, and and then it displays the score. This was the idea. So what we have done is we built the University of Manchester this technology called electronic nose on a PET substrate, very simple print. They use inkjet and other techniques, extremely low cost, a sensor array, electronic sensor array. So it's sensitive to organic volatiles, whether it's an armpit or any other smell. And Pragmatic and ARM, we build a mixed signal IC, the sensor interfacing the sensors, and then a machine, very simple machine learning, just predicting the malodor score. When the smell exposed to sensor, the data is coming to the chip. Chip translates into digital and provides to ML. ML says this is score 1, which is okay. Well, if it is 5, it is very bad smell. That was the simplicity of it. So we built this chip using Pragmatic's older technology, 0.8 micron. You can see that the chip was quite relatively big and consuming power at 5 volts. And this was a hardwire ML, so meaning that this was only, this chip can only work for the specific use case. Just checking the time here, okay. So the second example is another hardwired ML example. This was again collaboration between the University of Manchester, but it was a different group, and Pragmatic. So what's a tiny classifier circuit? So it's a circuit representation of an inference engine directly generated from the data, tabular data. So it works for the tabular data. So we use an evolutionary technique called EGGP, evolving graphs by graph programming. And what it does is that you take the tabular data, it could be any tabular data, and you want to create a hardware that does the inference. So we are generating the inference hardware directly from the data. So this an evolutionary algorithm starts with a random circuit, and it evolves this circuit in a typical genetic algorithm way. So finally, And the fitness function is a prediction accuracy. When the prediction accuracy maximizes or there is no further improvement, then you stop. The final generated circuit becomes the inference circuit for that specific tabular data, and then they translate it into Verilog automatically, and you can put it through the ASIC flow. So here, all the work done by Manchester University in terms of model development. So we, as Pragmatic, we did the chip implementation and fabrication and test. So, obviously we can't build multiple chips for each data set. So we choose 2 data sets, and we build the tiny classifier using our 0.8 micron, which is an older technology. To compare, to get a baseline as well, the same data set, we use a conventional ML algorithm like in the XGBoost shown here, build a chip, again, using the FlexIC, so you can see the comparison. Here, so it's a dramatic improvement using the tiny classifier circuit. So for this example, it's only 10x power and area improvement, but for that data set, it was like 75%. So this was a nice exercise to use our technology. The last example I want to give about hardwired ML is so another collaborative work called RWIN. So this was an implementation of a weightless neural network. So I will briefly mention what weightless neural network is. So it was so the model. So the weightless neural network has something called RAM nodes. The RAM is essentially an SRAM, but it learns the logical during the training. It learns the logical functions of inferring from the data, the training from the learning from the data, and during the inference, those RAM nodes are converted into Boolean functions. So you don't actually implement any memory or SRAM. You just convert the learned weights into logical functions. So the entire circuit can be fully combinational logic. That was the idea. So build something as optimal as possible. So the model development, the inference hardware design, and the implementation was done by 3 universities, so UFRB from Brazil, and UT Austin, and UT San Antonio. Again, our role here was very simple. We just, like a foundry model, we get the design from them, from the partners. We fabricate and test it for them. So the chip is shown here. So we use here our latest technology, 0.6 micron. You can see that there are improvements in the area as well as the power. The clock speed is 100 kilohertz. You may find it a lot slower, but it's good, sufficient enough to do the job. So you don't need a megahertz processor there or a processing engine. So moving into the last example from the domain-specific processing element is an ASIC implementation for another healthcare application. So this detects the atrial fibrillation. This is not ML. It's just pure. The algorithm is implemented for detecting AFs, and we just translate this to an ASIC implementation. So the vision is that in the future we are envisioning an ECG patch like that. Everything is composed of all flexible printed components, from electrodes, ECG electrodes, to battery, may possibly display, and then flex ASIC like this. So we build this again using our latest technology. You can see that the power numbers are a lot smaller now compared to the 0.8 micron. So still a super small chip. So I have some samples if you want to see how they look like. This is the wafer, but I have also diced chips for this one. So I'd like to pause a minute, so share some, take your attention to something important. So if you notice the common feature, what I presented in the domain-specific processors, they were not programmable. They are just the hardwire design. So is this a disadvantage? Maybe a lot of you will say, okay, oh, you know, it has to be programmable. I will argue that it's not a disadvantage because a lot of these applications in the extreme edge, the products are short-lived. They have a short lifespan. Like take, for example, FMCG. Like milk, butter, or food package, you buy meat or vegetable. What's the lifetime of that thing? Maybe days or weeks. And if they have embedded FlexIC, the lifetime of the FlexIC also that short. So why would you program it? Why would you make that programmable? So I will say that designing hardware FlexIC makes sense, but does it make economical sense? So this is another question. And I will say that yes, for FlexIC it makes sense because we can fabricate these things if the volume is right, a lot faster. If you imagine, if we can, obviously today is 4 weeks for us to manufacture these chips, but we will improve to days. So imagine that we can manufacture hardware designs in days. So design and manufacture them in, let's say, days or weeks. And low cost as well. So the one example I can give is the armpit, the smartwatch. So let's say we build the smartwatch with the hardware ML, and a week later, the company who's producing those smartwatches, they improve the ML model. So what will happen is that, because these are very fast consumed goods, right? Next time around, they will send us the updated weights, and we manufacture a new hardware ML with these updated weights and integrate it into the new products. And this is actually quite efficient in terms of cost and time. And this is something different. This operational model doesn't exist in the conventional silicon world. I don't know if I make myself clear. Maybe it's okay. Great. So let's talk about so far I look at the prototypes we will in the domain-specific for domain-specific extreme edge applications. So I will look into the general purpose. So these are more suitable for applications, extreme edge applications that have longer lifespans. So the first one is the legacy CPU we built. So maybe some of you remember the 6502 8-bit processor. So this was actually done before I joined Pragmatic. So Pragmatic collaborated with HiPEAC and KU11 to build this CPU. This was built using our older technology, 0.8 micron. It was a relatively small design, about 3,002 gate equivalent. And it was running pretty fast because of the pseudo CMOS libraries, the KU11 design. And this one was built when actually I was at ARM. So my colleagues were collaborating with Pragmatic at the time. So this plastic arm is the first SoC system on chip design in Pragmatic's technology. Again, it was used, it was built using the older technology, and this it's Cortex M0 based, so it's actually quite product quality with some minor modifications. It wasn't running too fast, 30 kilohertz, but I think it's something expected in our technology. So you will run it maybe from up to 100 kilohertz is the maximum you can get if you use 0.6 micron today. And this was actually published in Nature about 4 years ago. And one thing I like to say that although I categorize this as a general purpose, the SoC had a ROM, and ROM had 3 test programs. So this was not actually, you couldn't actually compile programs and run on it. So it was only running the 3 test programs. But it was a good step because nobody has built a complex processor using our technology before like this. So that was a big step. So I will now focus a lot of the rest of my talk on the FlexRV or Bendable RISC-V processor. So I like to say one more thing here. So so far the prototypes I show you about domain-specific general purpose, they were built, fabricated, but they were tested on wafer. And there was only plastic armpit. I think we diced it and integrated on a rigid PCB, just to show that is a proof of concept demonstrator. So none of the work we have done, I presented before, are assembled onto a flexible PCB and actually demonstrate the functionality while it's bent. So, but here in the FlexRV, we will show and we will address all these things we haven't done before. So this was again, I think I summarized. So the first non-silicon RISC-V processor. I guess we can claim that. And it's also an SoC, and difference from the plastic arm was that we also integrated a very basic small ML hardware accelerator tightly coupled to the CPU. And we assembled this to a flexible PCB. I will show the results, and there's a video as well. So I have to note that this was a collaboration. You know, again, all of the work we have done so far, you can see that we are a very collaborative company. So Harvard and Camcom were instrumental, especially Camcom. It's a Swedish company, and we were in touch with the gentleman called Olof Kindren, who designed SIR, which was what we use in FlexRV. It was published in Nature last September, so we got some media attention, but most of them were witty remarks like bending the rules or bend it like RISC-V and etc. So let's dive into the system architecture. So as I said before, we used serve, and servant was the starting point for us. So we didn't want to go design a RISC-V processor from scratch. So we modified the servant SoC to create a FlexRV. So there are some minor modifications we made, like the serve supports RV32i. So we added, we supported RV, we changed it to RV32e because we want to reduce the number of registers. I think I didn't mention, but if you don't know, so serve is a compliant RISC-V, 32-bit compliant RISC-V processor, but it's a bit serial microarchitecture. So it can run any software compiled for RISC-V, but it executes everything bit by bit. It's extremely slow. You have to run this extremely at high clock frequency not to see the difference. So, but for us, it wasn't important. So high performance is not a requirement here. And we added ML accelerator as well. And the other thing we've done is that you can see that servant has on-chip RAM. We don't. So the reason is that today we cannot integrate large on-chip memory in our technology, which we are working on. It will happen. Here, large means not megabytes. I'm talking about even kilobytes here. So what we have done is we use an off-chip memory to get the program and the data into the chip. Instead of going parallel to the off-chip memory, this is also very unusual. we use an SPI, serial peripheral interface. So the reason for that is that we like to keep the number of off-chip pads to a minimum to simplify because we like to assemble this chip to a flexible PCB, and this was not done before either. So we are trying many unknowns. For the first, doing many things the first time. So we didn't want to risk that. So we wanted to keep the number of pads small. So that's why we use an SPI. So even the memory access, you go in bit serial way. So very quickly, this is how it works. So when we build the chip, this is how we test it. We connect it to an FPGA. FPGA essentially emulates the off-chip memory, but also supplies the power, the reset, and the clock, and then gets the GPU general purpose input-output as an output from the processor. This is where we get the running result. If you run a test program, the result is coming through the GPIO interface to FPGA, and then shown on laptop. So the SPI is a bit. We had to change custom SPI because we use it as a memory access, which is unusual thing. It's not done before, and if there's a long memory access time is off chip, so you have to stall the CPU. So there was a clock, gated clock to stop the clock to CPU every time you access a memory. So these things slow it down, but for us it didn't matter much. So we added very simple ML accelerator. It was a SIMD base. This was done actually by Harvard, and it's tightly coupled to serve. So we added about 4 instructions to the ISA to program this accelerator. Just checking the time again. Good. So we implement the chip. So this is how it looks like. We managed, so there are 20 pads here. We managed to squeeze 2 FlexRVs in one chip. So, at least, if one doesn't work, we can try the other one. This was built using our latest 0.6 micron technology, about 18 square millimeters. Is it too big? I don't think so. So it can fit into many patches and swatches and everything. So implementation clock frequency 61 kilohertz, consuming less than 6 milliwatt. And it was relatively big design, 13,000 NAND2 equivalent gates. So this was also another milestone for us. Some test kernels, we had to write these test kernels in C, compile and run. And the last 3 ones, we particularly selected so they use the ML accelerator using those instructions we added. So this is what happens. So these things we learn. So when I move from ARM to Pragmatic, now you don't just build RTL, but you actually fabricate and you have to test. So the first thing we have to do is test the design, the fabricate things at the wafer level. So we have wafer probe stations, the wafers come and we test the wafer automatic. It's like a semi-automatic. So why we are doing this, we have to identify the good known dies from the wafer. Some work, some don't. So you need to identify the good ones. Once you identify the good ones, you tell the dicing team to dice them and integrate it into a flexible PCB. I don't know if you can, I have the same one here. I'm holding it. So this one is the big one is the PCB. That little rectangle is the chip. So we don't do the PCB. You can get it from anywhere in Europe or in Asia, the PCB manufacturer, but the chip assembly is done in-house. Yeah, I mean, what we are doing is the chip facing up facing up and using some non-conductive adhesive. It's also different from silicon chip package. So bare die is face up. We don't do any kind of plastic packaging or anything. This is this one comes directly from the wafer, attached like this with a glue, but it's non-conductive. And the pads are aligned, so there are metal pads on the PCB. They are aligned. We use inkjet printing to connect the pad on the die to the pad on the PCB. There's also some adhesive in that ink, so it connects together. So you can actually band. So you don't need to do extra packaging in the sequence. That also another factor to reduce the cost. So there's no special packaging required. So moving on. So these are the performance results. So performance here is the clock frequency. So we measure the maximum clock frequency. We can run all the test benchmarks. So I can tell you that the average is 52. We tested so many of them. Maximum 60 kilohertz. So that 60 kilohertz is actually matching the implementation. As I said before, 61 kilohertz. So that was good results. So you can see the table. I mean, I don't know how visible it is, but these are the execution times. So it is on the orders of seconds. There are two reasons for this. First, it's a bit serial CPU. Everything is executed bit serially. If you're executing bit serially, you have to run it very fast. But this one, it was running at 60 kilohertz. The other one is the memory is off chip, and memory is also bit serial. So if we can resolve these two issues, the run times will improve significantly. And this is where what we are working on. I will talk about it if there is time. This is the most interesting bit. No one has done this before, so we actually take this multiple of these PCBs. Maybe I forgot to mention. So this is the FPGA board. So this PCB is connected to the FPGA using this interface, and then a GP. So this is the UART interface connect to laptop. I think I forgot to mention that. So this is how we do it. For bendability tests, so we use non-conductive cylinders with a different, different cylinders with a different radius of curvature. So what we have done is we roll the PCB around this. You can see the picture. I have video as well. So we bend it. So for example, one way is to bend it like this. What we call it tensile mode. The chip face up like this is bent like that. The other way is called compressive. So when you roll, so you are actually bending the chip inward. So this is called compressive. So we like to see what's the performance change or not. So what we have done is we run the same test kernels to measure the maximum frequency. So interestingly, if you run it on tensile mode when the chip is like that, it gets about 2% faster. The maximum clock frequency, you can clock them faster, but if you compress them, and on average, it's 4%, it gets 4% slower. This is a very, very interesting phenomenon. I think at the transistor level, the researchers done this, taking one of the IGZO, the transistor, which is what we use. They do this band test, and they see that the transistor mobility or the threshold voltage changes with the mechanical stress. But at the system level like this, it was the first time we have done this, and our tests were very rudimentary. Right? So we buy cylinders and then roll this PCB just to test. So there is more research needs to be done to understand why this happens, and can we actually utilize these interesting phenomenon to speed up or so what's next? So what are we working on? So right now I will talk about two more things, and then my final slide is coming. So we are working again with the two partners, Newcastle University and Literal Labs. Literal Labs is a startup in the UK. So they are developing this interesting machine learning paradigm called settling machine, and we like to, as Pragmatic, to build a FlexIC for that. So this settling machine, in summary, so it was invented by some Soviet scientists in the 60s, and revived by Norwegian scientists recently. But Newcastle professors recently built a very efficient hardware implementation of settling machine, and they've been publishing, and they commercialized that technology. So under the name of Literal Labs. So Literal Labs is essentially commercializing the methodology. What we like to do is, as Pragmatic, obviously, we are sitting back, foundry, bring the design, we'll fabricate for you, and we can test. So how it works is also it's very interesting. It doesn't use complex arithmetic. It's just gates, C of gates, which is what I like to do as well. So get the raw. My laser pointer is not there, so they take the raw data set, and what they do is they use an algorithm to Booleanize these data sets into Boolean features and their complements. And then the decision block has multiple clauses, and each clause is essentially bunch of logic gates, and these Boolean features called literals. That's why the company is named Literal. Controlled by a single input, whether to include that literal in the clause or not, include or exclude. So that include, exclude learning is done by an automaton called settling automaton. So this is the training. It can do online training as well. So it's an interesting, or you can after the training, you can do offline training and then stop and then just implement the inference engine in hardware, which is in this case just Booleanizer, decision block, and the backend, which is the thresholding and voting, etc. This is all very standard, simple gates, C of gates. Very efficient. They show that as well. The company is commercial, so I'm not going to go into that, but this is something I like to see as well. And the group in Newcastle is also a specialty in doing asynchronous design. So I'll be interested in seeing this, doing clockless FlexIC, essentially running this without any clock. This is the last slide before my conclusion. So now we are working on the first bendable microcontroller unit. So this will take time. It will take 3 to 4 years. So now we are designing our own RISC-V processor, but our approach is slightly different. We like to do some kind of customization here. Don't use all the instructions, just to use the instructions you needed for the application type of thing. It's in the work in progress. But we will have all the other blocks and MCU as like the sensor readout interface, analog front end, and NFC interface. So what we like to do is, next, after building the MCU, we build a compute device using all flexible components coming from different partners, like printed sensors, printed batteries. Essentially build a very tiny compute platform that can be programmed through NFC. We will also, you can imagine like an Arduino platform, but you use your smartphone to program it, and it should be extremely low cost, maybe less than $1, the whole thing. And we will have some memory, on-chip memory as well here. We didn't have it in FlexRV. Now, so skipping, so this is just a summary, but I like to share with you some of our experiences and lessons learned when we design hardware with a new technology. As Kun described, so my background is also coming from the silicon world and all the biases, right? So I think the common mistake we make is that, we come from the silicon industry, a new technology, let's do this, let's do that, but there are, this approach is not right. So we we need the delicate balance, how much we can borrow from the silicon industry in terms of supply ecosystem and tools, etc., right, to a new technology. So one example I can give is, I mentioned this, the supporting, integrating your technology into any commercial EDA tool flow. So this is standard way of doing this in the silicon world, and we can do it. This is a good thing to borrow. But if you want to, the flexible electronics, let's build a system on chip and put all the peripherals there for any application, so that we don't have to worry about there is some, we can run any application for using that micro. That's not the right approach. You need to understand the capabilities of the technology and what applications it is targeting. You're not going to build a general SoC with all sorts of peripherals and caches and blah blah. This is not the right approach. So we learned this during the process. So what I call, what I suggest is that when you're working with a new technology, so you need to be working in what I call bias filtering mode, so that you don't overborrow from your past. You need to filter properly. The other thing is that there is no Moore's law driving the flexible electronics, as you see in my presentation. So we are using 0.8 micron. This is 800 nanometer technology, channel length of the transistor. Our latest is 600 nanometer. Why are we not going lower? Can we go? Yes, we can. Why are we not going? It's a lot lower cost, and it does the job. When it doesn't do the job, we move. This is our approach. And another example is that when we started plastic armpit project with the Unilever, it was in 2017. And I was at ARM, so the Pragmatic told us, your budget is 1,000 gates. We can build more than that at the time. And we had to innovate on the algorithm side, on the microarchitecture, so that we can build something that can fit into 1,000. Today, we take it for granted. Well, I have the latest ML algorithm. I'm going to build a 2 nanometer chip. Transistors are free. It's not this is the bias again. So you need to understand the domain and the capabilities of the technology before you jump into it. One more thing is I think I mentioned this as well. So FlexIC technology enables the low-cost design and fabrication. So this is unique. So I think this is very difficult for the silicon, especially on the timing side. The other one is, the last one is, I think we show that the bendability of this is a unique feature, so we need to have the bendability as a design constraint, similar to in silicon world we have the PPA, the power performance area, but when you're building a bendable processor, I think people need to add bendability as a design constraint and do more analysis. I think that is it. I hope I did it on time.